Dite lui di rimanere all'inizio per l'esecuzione.
Hello? Duplica? Hello, welcome to this virtual training course of the European project HERACLES, devoted to preventive conservation of cultural heritage structures. This virtual training course is entitled Geomorphological and Structural Modeling Applied to Cultural Heritage Management. We are at University of Perugia, and with us there is our partner, that is e-Geos, company e-Geos, and we will have 3 speakers today for this virtual course. We will start with Dr. Mario Costantini from e-Geos, that will be the first speaker. Then we will follow with Dr. Veronica Castaldo, second speaker, and finally myself, Professor Filippo Ubertini, that talk as a third speaker. So I will now invite Dr. Mario Costantini to give his presentation. Just let me a second to switch the slides.
No, è stata caricata.
Sarà questo? Ok. Se vuoi questo, puoi usare. Okay, Mario, I give you the stage.
Good morning to everybody. My name is Mario Costantini, and I will speak about satellite radar interferometry. I will give an introduction about this technology, and then I will show several applications. So let's start with the basic principles. The idea is to observe the ground from satellite with a particular type of radar called synthetic aperture radar. And these sensors are characterized by imaging the scene with a coherent type of radiation, microwave radiation, but what is important, coherent radiation. So this means that you can perform interferometry, is the kind of phenomena that you observe when, for example, you throw 2 stones in a lake. You will see the interference between the waves, and by exploiting this interference, it's possible to make measurements that correspond to a fraction of the wavelength. Since this system, this microwave radiation, the wavelength is a couple or few centimeters, you can measure millimeters. Even though you observe the scene from several hundred kilometers from satellites that are several hundred kilometers above the Earth, you can measure millimeters on the ground. The typical interferogram you obtain, you see here a typical interferogram. The fringes, the interferometric fringes, give you information about the elevation of the scene. You can see here the Vesuvius volcano, and these fringes looks like contour levels that give you an idea of the elevation of the height of the volcano, but also they provide you information about the possible deformation that occurs between different acquisitions. And in fact, you will see in this area, the Campi Flegrei area. This is an area characterized by volcanic phenomena called bradeism, that make the terrain going up and down, and you will see that these interferometric fringes give you information about these deformations. More, to let you understand better what happened, let me show you a scheme of the process. Assume that you observe the ground with a fast satellite acquisitions, and assume that after this fast acquisition you have a deformation of the observed scene. When you perform a second satellite acquisition, exploiting the fact that, as we said, these radiations, these images are made with a coherent radiation, you can perform interferometry, and this means that you can measure the phase difference between the two signals, and the phase difference contains three contributions. The first one related to the different position from which you observe the scene, because the satellite orbit is not repeated exactly. Typically you have a few hundred meters distance between the acquisitions. Typically this is called baseline, this distance. Then you have a second component of the phase difference that depends on the fact that at different dates you have different atmospheric conditions, and so you have different delay of the signal for the propagation through the atmosphere. And a third contribution, which is probably the most interesting, is related to the deformation. This is probably the most interesting signal, but even the contribution related to the different position is very important, because this provides you a kind of stereoscopic vision that it's important to determine the three-dimensional position of the target and the three-dimensional position of the measured deformation. So you are able to localize the exact point where the deformation happened. Now, this is, even though the principle is very simple, extracting this information requires a quite complex technology. First of all, you need to have a coherent signal, but only few sparse points really return coherent signal, because strongly vegetated areas, due to the movement of the leaves, doesn't provide a coherent return, because the scattering mechanism, the scattering surface change with time due to the movement of leaves. So typically coherent signal is returned by bare soil or corresponding to buildings or rocks, and this point must be found as part of the processing. As we said, we have three main contributions to the phase difference, to the interferometric phase, and these three contributions need to be separated and recognized, because they are mixed together in the interferometric phase. So you don't know what is deformation, what is elevation, what is atmosphere. You need to separate to recognize what depends from the deformation, what is depends from the elevation, and so on. An important point is that the interferometric phase is ambiguous. You measure only the fractional part of the phase, and you have an ambiguity corresponding to an integer number of wavelength, and the process of resolving this ambiguity is called phase unwrapping, and it's a very, very difficult process. And typically we don't use, as in the example I showed you, in the sketch I showed you, only 2 acquisitions. We use a series of acquisitions, first because we want to observe deformation for long period of time, but also because without this series of acquisition, it would be impossible to distinguish these 3 types of signals, and would be impossible to achieve very precise results. If you use only 2 acquisitions, you can measure only very, very strong deformation, but you are not able. But very small deformation would mix. You would not be able to distinguish small deformation from atmosphere delay or other effects. So we said that the technology is very complex, and we developed. There are a few approaches available in the literature. We developed a method called persistent scatterer pair. The name comes from the fact that we exploit only the relative signals between pairs of points that are not too far one from the other. And the reason for doing this is because atmosphere is spatially correlated, and typically the atmospheric disturbance is not it's the same for points that are quite close in the space, and so in this way, with our method, we are intrinsically not affected by this atmospheric disturbance, and also our method is more robust to and more powerful to more robust to spatially correlated signals, which can be not only atmosphere but also other effects. I will not go here into too many technical details. Another qualifying point of our approach is a very robust method for finite difference integration and phase unwrapping, which I told you is one of the more difficult problems about star interferometry. And with our method, we exploit redundant information from a non-planar graph, which can be a multi-temporal three-dimensional graph, and this guarantees again more reliable and accurate solution. And also this redundant information from these multiple arc connections between nearby points makes for extracting the coherent information even from weak signals, both from point-like scatterers, but also from surfaces characterized by distributed scattering properties, but differently from approach called distributed scattering techniques, we are able to keep the full resolution of the signal. This Ma prima funziona?
Sì, sì, sì. Vai. All right.
So, sì, ma it's not working. It's not. Okay. Okay, so sorry, there was an interruption in the connection. I hope you. I think we arrived at this point. So I was saying that this processing typically requires high-performance parallel computers to process large areas in a reasonable time. And our technology was validated and used in several applications and massive production, and we will see a lot of examples. Just a few words about the processing parallel processing system that we use. It's a cluster with about 2,000 nodes, and a couple of years ago was the state of the art of this technology, and is a modular structure, easily expandable, and also using external systems, cloud systems, and in the future we plan to pass to a system that will use a mixed solution, an internal cloud and also external clouds. The applications of these technologies are many. All applications that involve ground deformation measurements, from subsidence phenomena, landslides, volcanic phenomena or earthquakes, deformation related to mining or underground excavation activities, or related to oil and gas or water extraction. And with the modern satellites, in general, structural and infrastructure monitoring, so highways, viaducts, railways, pipelines, dams, industrial sites, and even each single building. The typical product consists in a set of measurements. Each measurement is precisely localized in the three-dimensional space, and for each point we provide the mean velocity between the first and the last acquisition, SAR acquisition, and typically this mean velocity is represented with colors, and here you can see an example of color bar. And for each point you can also we can also provide the deformation at the different acquisition times, and this is important to observe possible accelerations or deceleration of the movement. Here is an example of measurement in an urban environment, and you can see that as we said, I already mentioned, we not only have measurement corresponding to the corners of the buildings. The corners provide a very good return, a very good signal, because corresponding to the corners you have double band scattering, but even relatively smooth surfaces, like in this case the surfaces of the square, the Plebiscito Square in Naples, provide, even though the signal is very, very weak, because flat surface act like a mirror, so the signal doesn't come back toward the satellite, but go out toward the other direction. So even though the signal that come back to the satellite is very weak, you have a very good we are still able to get measurements. Or this is another example in a mountain area. As we said, it's not possible to get coherent signal in the strongly vegetated areas, but corresponding to grassland, we have very good signal. And this is a nice example showing the coherence in a. This is a rural area, cultivated terrains, and you can see that corresponding to the fields where in the period of acquisition we acquired the images from April 2012 till October 2012 in this case, and in the parts where some agriculture work were performed, we don't have at all coherence, and we don't have any coherent signal. On the contrary, in the part of the fields where there was no agriculture work, we have a lot of measurements. Now, some words about the accuracy of these measurements. We performed several validation tests in several types of terrains, from urban areas to grassland to rural or bare soil areas, or even corresponding to infrastructures and so on. And typically the standard deviation of each single measurement is between 0.5 and 3 millimeters. And typically this with a very high density of measurements, several tens of thousands of PS per square kilometer. If we use more conservative thresholds and we select less PS, of course we have better signal-to-noise ratios, and we are more close to the 1 millimeter accuracy. If we want to have very high density, we are around 2 millimeters on the average as for the standard deviation of these measurements. And it's important to say that this is the accuracy on the single measurement. About the mean velocity, this accuracy, of course depends on the length of the observed period. So typically, if you want to measure the trend in 1 year or in 2 years, the accuracy in millimeters per year, of course, is the accuracy on the trend is much better if the observation period is longer. And it's important to have a sufficiently long observation period, typically at least 1 year, also to distinguish between real deformations, trends, or seasonal trends related to seasonal thermal deformations. And we will see some examples. Another important point to notice is that these are the millimetric accuracy is about deformation. About the positioning, the three-dimensional positioning of the point, the accuracy is metric. And this is very important because we are able to determine which part of the structure is subject to a deformation. Now, some characteristics of the satellite measurement that it's important to know, to understand and to interpret these measurements. All currently available satellites are on sun-synchronous polar orbits. This means that you have two types of acquisitions, ascending and descending acquisitions, but all these acquisitions, all the orbits are typically north-south. The track of the orbit on the Earth have north-south direction, and since synthetic aperture radars line of sight is on the side of the track, And since the measurement that we perform is along the line of sight, typically these systems are very sensitive to vertical and east-west displacements. On the contrary, there is not good sensitivity for the north-south movements. Some techniques exist to measure north-south movements, but the precision is not millimetric for this north-south movements. On the contrary, we have very good sensitivity for vertical and east-west deformation. Another important point is that what we measure is the component of the deformation along the line of sight. So if we observe these two landslides along in these two slopes in this valley, so the component of the landslide along the line of sight can be a movement that is approaching the satellite or going far away from the satellite. So what we measure is the red or the blue arrows. And when we observe with the other geometry, this is ascending geometry, when we observe with the other geometry, we have this complementary situation. And typically, for example, these are real images, real measurements. This landslide here has a positive velocity in this geometry and negative in this other, and the opposite in the other slope. By combining ascending and descending geometry, it's possible to reconstruct the eastward and the vertical component of the deformation. And of course, this is possible only for the points where you have both the measurements. When the slope is very steep, typically you have only one information, because very steep slopes can be observed only with either the ascending or the descending geometry. A few words about the possibility of having measurements also on strongly vegetated areas using artificial reflectors, corner reflectors, and also the possibility, and also about other technologies that exploit not the phase but directly the amplitude images to measure very fast movements that could not be observed by phase interferometry due to phase aliasing if the movement is very, very fast. Here you have an example of a movement that it's few meters. In this case, you could, between two acquisitions, in this case you could have phase aliasing also because there is a very abrupt change between the area subject to the movement and the stable areas. And for this technology, it's possible to exploit, to track the offset from the amplitude images. Now, let's pass to examples. I will try to go very fast because not many to not use too much time. First, the first project at a national scale that was performed in the world, and this was performed in Italy. We processed the whole ERS and MVSAT archive of the whole Italian territory, and then we updated this measurement with the high-resolution Cosmos SkyMed satellite. Some numbers: we processed more than 20,000 images, obtaining something like 10 billion PS ground deformation measurements covering the whole Italian territory in the last 20 years. And these measurements are available to the public through the National Geoportal of the Italian Ministry of Environment. Now, some words about the new satellite that was launched by the European Space Agency, called Sentinel. These satellites have the characteristic of covering a very large area. So this is possible with relatively short, very easily to cover very large areas. But of course, this has a cost, because here you see an example of Cosmos SkyMed result along some railways. You can see the measurements that are very well located along the railway. On the contrary, with Sentinel, the resolution is not good enough, and the measurements are not very well located, so you can have only a kind of aerial information. Another example: Cosmos SkyMed points very well located along the structure of a tower. With Sentinel, you obtain only few points, quite sparse. So with the Sentinel, you cannot perform, it's not very useful for structure monitoring. You cannot perform monitor structure like this. You can see the very well location of very good location of points along this bridge with Cosmos SkyMed. Or this is a very nice example of reconstructed, where the structure of electric towers are very well reconstructed using Cosmos SkyMed high-resolution measurements. And this is important because, as you can see from this example of the tower, the electric towers, the deformation in different points can be different. For example, it's very clear here. At the top, you have seasonal dilations that are very clear due to thermal dilations. And as expected, on the bottom of the tower, you don't have these thermal dilations. So these examples show you that it's important to distinguish different parts of the structures. Here is another example. This is a building located in Rome, a building that collapsed in 2016, and it was possible using Cosmos SkyMed high-resolution measurement to see that one side of the building was going down and the other side of the building was going up. So the building was kind of rotating. And also you can see here from the graphs that till 2012 the building was quite stable. Then one side started going up, the other side starting going down, and in the last year there was an acceleration, and at a certain point they collapse. So to monitor structures, it's very important to the possibility of measure differential deformation between the different parts of the building. This is a comparison table between the characteristics of Cosmos SkyMed and Sentinel, which, as I already said, are quite complementary, because one is very useful for very large areas. With Sentinel is potentially possible to cover entire continents. On the contrary, with Cosmos SkyMed, you can monitor you can perform very detailed analysis of structures, or like building infrastructures, and also monitor critical small landslides. There are also some other satellites available, and in the next few years there will be many new satellites, satellites, including small satellites constellation from private companies, which will increase the current capabilities and will open new applications. Now I will go very fast through some examples, starting from subsidence related to water and oil and gas deformation. This is the area of Emilia-Romagna in Italy, with strong deformation due to extraction of water for agriculture and industrial activities, or due to gas extraction from offshore platforms. This is an example of monitoring of an aquifer in Madrid, where they put water in winter and extract water in summer to supply water to Madrid. And you can see the very good correlation between the piezometric level of water and the subsidence measured by satellite. Some example of mining sites, ground deformation due to mining activities. This is another example in the Italian Alpi Apuane for extraction of Carrara marble. Some examples of landslides, where you can see that the advantage of high resolution is not only density of measurements, but also the possibility of seeing some phenomena that were not visible with the low resolution images, because thanks to the high resolution you can penetrate in small spots of bare soil between the vegetation. And this is an example of monitoring of an infrastructure, a railway in Russia, which is affected by a strong problem, because the railway, there are many landslides just along the track of the railway. An example of landslides in Italy, close to the Morvanno tunnel, Morvanno, and it is interesting to notice that this landslide was activated by a small earthquake occurred at this date. Before, the landslide was quite there was no movement, and the smaller quake triggered the movement. Some example of the infrastructure monitoring. This is a viaduct. You can notice the very good localization, three-dimensional localization of the measurements. Another viaduct, and you can notice the deformation related to seasonal thermal dilations. On the contrary, you here have real deformation due to compaction of terrain in this ramp, bringing to a bridge in the ring around Rome. This is the Rome Fiumicino Airport. You can see that the airport track is affected by subsidence, and you can see that by satellites you can really see very well each single part of the track. Subsidence along the highway bringing from Rome to the airport. And this is interesting to notice that here is the crossing between the Rome highway ring and the highway that brings to the airport. And corresponding to the crossing, we have very deep pillars, and so there is no subsidence. You can see that here the color is green. On the contrary, the rest of the highway is affected by subsidence. This is subsidence related to the excavation of the subway in London, underground excavation activity that cause terrain subsidence. Even more evident in Shanghai, because the subway is less deep in the terrain, less deep in the underground, so more effect. Landslide along a road, a small road. Landslides in the basin of Mont-Cenis Lake, at the border between France and Italy. It's important to notice that by satellites it's possible to monitor not only the structure, the dam, which is monitored probably by field instruments also, but it's possible to monitor also the surrounding area at relatively low cost, which would be very expensive to do by traditional field instruments. This is the famous Mosul Dam, and which is became famous because for reasons related to the war in Iraq. Some example of urban areas monitoring. This is Beijing in China, and they extract a lot of water, and they have a very strong subsidence phenomena with problems to the buildings. Another Chinese city, Wuhan, and I will just pass these slides because time, otherwise we use too much time. again, problem to the buildings in this Chinese city. This is another Chinese city. Chinese cities have strong subsidence problems, but even in Italy we have subsidence problem. This is Rome, and in the areas along the river, Tevere River, the type of terrain is subject to compaction and subsidence. Finally, I will say just a few words about earthquakes and volcanoes. This is the area of the Campi Flegrei, and we have this is the east-west component. In the last period, we have a kind of dilation of this area and vertical uplift of the area. So this is an enlargement, dilation, and vertical uplift. And this is a comparison with the GPS measurement in the Campi Flegrei area, and you can see that the agreement is very good. It's possible also by satellite interferometry measure deformation related to earthquakes. This is post-seismic deformation in the area of L'Aquila, Italy, and we just performed together with the Italian National Institute of Geophysics some experiments, and we also detected some pre-seismic deformations, which of course is very interesting. Now, just the last slide about the Gubbio project that we are affording in the framework of the HERACLES project, and my colleagues will talk more in detail about this Gubbio project. Just a very few words. We have that the Consoli Palace is subject to small deformation, and my colleagues will go in detail about this deformation. And the idea is to have the idea that we are trying to afford within the HERACLES project is to build an integrated approach where we have satellite analysis and structural modeling, other type of field measurement like temperature, but not only, vibration and so on. You will see in the next slides, and to perform correlation between these measurements in order to be able these are the satellite measurements, and these are structural modeling and temperature measurements, and by putting all together, the idea is to have an integrated approach where the satellite provides a fast view on relatively large areas, and this measurement can be used for deciding which area are relatively not too much, not very critical, and can be in this area can be monitored only by satellites. The areas more critical then that are showed by the satellite measurement can be more in detail explored and monitored using other field instruments. And in this case, the satellite, the idea is to use the satellite as a first guess to decide where to put, to optimize the localization, to decide where to install field instruments, and in the case where the movement is not very critical, these areas can be monitored only from satellite. So sorry, I took my presentation was too long, and it's time to leave the stage to my colleagues. Thank you.
Thank you very much, Mario. I hope people can hear me online. So now we enter more into the details of the work being carried out in Gubbio within the HERACLES project. We will have two talks. The first one is by Dr. Cataldo, that will talk about material degradation and climate-related problems to materials in Gubbio, including future scenarios simulation. And then there will be another talk by myself on the structural health monitoring aspects. So now I leave the stage to Veronica Castaldo.
So thank you very much for the introduction. So I'm Veronica Castaldo, and I am involved more in the environmental aspects of the HERACLES project. So I will, in this brief presentation, I will try to summarize the main objectives of our analysis, which has the purpose mainly to investigate the local microclimate conditions of the sites, which are the case study of the project, and to understand which are the main, let's say, the most suitable strategies in order to mitigate such phenomenon, which is very let's say, dangerous for heritage sites and historical buildings, which are not so much resilient with respect to climate change related phenomena. So this is a brief summary of the presentation. I will briefly introduce the concept behind the project, and I will describe the approach that we have been using in order to study this phenomenon, and then I will describe in detail the case study, which is mainly the Palazzo dei Consoli in Gubbio, and then I will shift quickly to results and conclusions. So here, just a very quick overview of the project. Again, the name is HERACLES, so Heritage Resilience Against Climate Events on Site. And here you can see all the partners involved, which are composed both by academic and non-academic partners. And among the non-academic partners, we have not only municipalities, but also industrial partners. So in the bottom part of the slide, you can see the three case studies. So one of them is the Palazzo dei Consoli and the ancient walls in the city of Gubbio, which is the one I will be focusing on today. And the other ones are located in Crete. So we're talking about the Venetian fortress in Heraklion and the Knossos Palace. So, a brief description of Palazzo dei Consoli. We're talking about an ancient building which was built in between 1332 and 1349. It's more than 60 meters high, so it's a huge construction. And nowadays it's used as exhibition space, so it's a museum building. And inside there are a lot of artifacts from the 20th century. About construction materials, we're talking about calcareous stone. So here you can see summarized the main thermal properties. So we're talking about a conductivity of 2.2, a specificity of 840, and a density of 2550 kilograms per centimeters. And here you have other views of the case study building. So you're seeing the east-facing facade, which is the one hosting the main entrance to the building, and the one also mostly affected by the action of climate agents, as you can see from the picture. Then you have on the right the terrace, which is still also very important, both from an environmental and structural point of view. And then you can see the location in the ancient city of Gubbio. So the building is facing the municipality building, and it's, let's say, positioned on the main old square of the city. Here you have a brief, let's say, storyline, timeline of the building. So from, let's say, 1898 up to nowadays, and you can see how the, let's say, deterioration of the facade is changing over time. I highlighted one specific, let's say, year, which is 1990. Sorry. Here you can see that the facade was really very much affected by, let's say, climate events. So huge rainfalls, extreme rainfalls, and heat waves, stuff like that. And you can see that in this moment there was a first cleaning, complete cleaning of the facade. Now I show you some pictures from the geometrical survey of the structure. So you have here some sections of the building. This is the first floor, and you can see also the pictures on the right. So it's a huge open space area, hosting a lot of artifacts and let's say, works of art from the 20th century. Here there are some typical floors from the upper part of the building, which is still dedicated to exhibition area. And here again the architectural survey of the east facade, which is the main entrance, and the other two facades, the north one and the south one, so the side one. So, which is the motivation? As I anticipated briefly at the beginning of the speech, our aim is to analyze the microclimate condition in the proximity of the building and to understand how it affects the, let's say, building itself in terms of indoor thermal comfort conditions, in terms of like energy behavior, so how the energy performance of the building will be modified by different outdoor boundary conditions. Then, of course, we analyzed also the main pathologies and the decay of the materials, which was directly attributable to climate factors, climate parameters. And then, of course, again, we try to map the local microclimate not only in the proximity of the building itself, but in all the historical city area, so also including the city walls surrounding the city center. So the purpose was, after a primary assessment of all these aspects, these issues, we want to propose and identify strategies to be applied locally in the proximity of the buildings, but also in, let's say, at urban level, to mitigate such phenomena. So by making the buildings and the construction more resilient to climate change related events without neglecting their cultural and historical value. So this is a scheme of the methodology applied. We have a first step, which, let's say, consists of the thermal energy assessment of the behavior of the building, so parasolic onto the building, and then we have the analysis of the material decay over time due to climate factors. So the first approach was carried out at first by performing a continuous monitoring over time of the main local microclimate parameters. So we're talking about temperature and relative humidity firstly, let's say. Then we used the monitored value to calibrate numerical models that were elaborated by means of course, dedicated software. And then we generated different boundaries. So we tried to analyze how the construction behavior changes in past, current, and future climate conditions, both near future and far future, let's say. The same we did with the material analysis, so we tried to understand which pathology of the materials could be attributable to a peculiar modification of a microclimate parameter that was measured on site. So here we are going a little bit into details of the microclimate monitoring. We first positioned two different sensors inside the building in two different floors that were selected as typical floors, so representative of the real indoor conditions inside the building. Such sensors were able to monitor continuously every 10 minutes parameters such as air temperature and relative humidity inside the building. And this monitoring was performed during fall-winter 2016-2017. Then we use this data not only to calibrate the model, but also to generate a complete, let's say, reference year. So we generated a typical meteorological year to be used for our simulations for the past, current, future 2050 and future 2080 simulation and climate conditions. So here you can see some details. For instance, for the past climate condition, we use data from 1961 to 1990 in terms of air temperature, and from 1981 and 1990 for global solar radiation. Similarly, we did something like this approach for the current climate scenario, while for the future ones, we based our analysis on the, let's say, report part of the IPCC, which stands for Intergovernmental Panel for Climate Change, by focusing on the worst possible scenario, so the A2 scenario, which is the worst scenario for the future climate boundary in terms of overheating, so global warming, let's say, and in terms of pollution. So we are considering the worst case scenario in terms, let's say, also of gas concentration. So how it will be the climate in the future in terms of CO2, CO, and VOC concentration in the air. So here you can see some pictures from the first model we elaborated. It's a dynamic thermal energy model. We try to reproduce, of course, the geometry of the building as it was real, and we performed different surveys in order to understand all the set points of the AC systems. So we try to reproduce the characteristics of the building in a realistic way. So, for instance, the set point temperatures are 20 degrees and 24 for winter and summer. We modeled the real occupancy schedule of the building, which is, again, is a museum building, so there are a lot of visitors during the day, but there is no one at night, so we try to model this aspect in a realistic way. And we performed two simulations for each climate scenario, one in free-floating conditions and the other one with the HVAC systems turned on, so in controlled conditions. This is because our aim was to assess the indoor thermal comfort conditions and the energy behavior of the building in terms of heating and cooling primary energy needs. These are some details about the settings in terms of occupancy schedule, activity performed inside the building, and of course the internal gains, which are mainly constituted by the equipment inside the building. Going through the methodology, here you can see the approach used to, let's say, identify all the problems related to material degradation over the building facade. So here we identified that there are two main phenomena that occur into the building. So we have detachment of parts of materials from the facade, and this is mainly due to heavy, let's say, and frequent rainfall, and then we have some organic growth over the facade surface due to condensation phenomena. And here you can see a complete map of the east-facing facade, which is the one also in the main entrance, with all the other degradation of the materials that we identified. So there are some vegetation growth, some black rust, subbiological patina, and incrustation due to climate action and climate agents. As for the microclimate modeling, at first we, let's say, identified a weather station which is permanently installed in Gubbio, and we used those weather data as boundary condition for our model. And then, of course, we positioned other sensors in the close proximity of the two case study areas, so the Palazzo dei Consoli and the area of the city walls surrounding the city center. And those two sensors allowed us to calibrate our model, so to see if the model we reproduced was representative enough of the real configuration of the case studies. So here is a slide about the calibration. What we did basically was a comparison between the simulation output and the measured data to see if the gap was acceptable or not, according to some calibration indexes which are here summarized. So we have the MBE, which stands for mean Bayes error, and the RMSE, which stands for root mean square error. So we see that the values are pretty good, pretty acceptable. So our models, both the models, the building one and the microclimate model of the area, were calibrated, so were validated experimentally. So going to the results and discussions. So here you can see the results of the free-floating dynamic simulation. So in the first graph on the top part of the slide, you have the trend of the indoor operative temperature of the building in the different climate scenarios that we simulated. So the past, the current one, and the 2050 and 2080 configuration, so future ones. As we expected, what we see here is that going from the past to the future climate condition, we have a constant overheating of the indoor temperature, which is of course related to the global warming phenomenon that will occur from now on to the future. So in particular, we have a maximum gap of 4 degrees by shifting from the past condition to the future one, and we have a slightly lower one by shifting from the current configuration to the future one, because we are talking about 2.5 degrees of difference. If then we compare the current configuration in terms of climate boundary conditions with the future one, the near future one, we have a 0.5 degrees of temperature, but this is a constant trend. And such results are also confirmed if we plot the PMV, which is the predicted mean mode, which is a parameter showing the indoor thermal comfort conditions inside the building for the occupants. So from the, let's say, user perspective. Here you can see that in order to be within a comfort range, you have to have a PMV which is between -0.5 and +0.5. And you see that we are almost there, but in summer, in all the scenarios, we are out of it. And in particular, in the future ones, so in 2050 and 2080 projection, we have a PMV which is really high, which is 1.3 or 1.6, which is really high, and we are out of the comfort range. So we have discomfort inside the building, of course, in the summer months. If we give a look to the results of the energy simulation, so the dynamic simulation of the building in controlled conditions with all the, let's say, energy systems activated, what we see here is that in different climate conditions, by shifting from the past one to the far future one, we have a huge increase of the cooling energy need due to the temperature overheating, and a slight lower the decrease of the heating energy need. We are talking about primary energy consumptions in terms of kilowatt hours per square meter. So this is according to the expectation if we consider that in the future we will have a general but constant and gradual increase of the outdoor air temperatures. If then we give a look to the results of the, let's say, material degradation causes, here what we did was to understand the trend of specific climate parameters over the years to understand some local decay of the materials over the facade, so to explain them, let's say, and to have a sense of what will happen in the future. So here we plotted the rainfall events from the past up to, let's say, nowadays, and we saw that there will be an increase of the frequency and the strength of such rainfall events. These, of course, will generate the increase of relative humidity, and if we look at the surface temperature of the building facade, we also have an increase. And this is true if we plot the year-round trend over the north and the east facade in the current condition compared to the past one, and also if you plot a daily trend. So what we see in the future is that due to the increase of rainfall events, due to the increase of relative humidity with, let's say, coupled increase of outdoor air temperatures and therefore surface facade temperatures, what we see is that those phenomena that we observed, such as the detachment of the materials and also the growth of organic materials and vegetation over the building surface, is likely to be increased in the future years. So we must act, we must provide strategies in order to mitigate such problems and such issues. What we can do in order to mitigate such phenomena, we can provide a, let's say, schedule, a surface cleaning of the facade, which must be both chemical and mechanical, but not too invasive, in order not to, let's say, damage the architectural quality of the building, which is an heritage building. In this slide, you can see the last part of the results, which is related to the microclimate analysis, so the microclimate simulation we performed. This microclimate simulation did not include, as I mentioned before, only the building, but it included also the plaza, let's say the square of the building, so all the buildings surround it, also the municipality building of Gubbio. So here you can see at different hours of the day, so 8 a.m., 12 p.m., 4 p.m., and 8 p.m., different maps going from the 2020 to the 21, like the 2100 years, and what we can see is the temperature difference in between the different years. So different boundary conditions in terms of climate. And it is evident how there is a constant, again, increase of such temperature difference. And we have a, let's say, maximum of 4.5 degrees by going from, let's say, the past 20 years up to the 2017 and so on. So this is also confirmed by the plot of the PET, which is the physiological equivalent temperature, which is a parameter that shows the outdoor thermal comfort of pedestrians. So people crossing the square, people hanging out in the streets because proximity of the building and so on. We can see, if you look carefully, that the plaza in between the two buildings is always getting hotter and hotter, so we have a huge increase of surface temperature and of the PET from going to the past years to the future ones. So if we have to, let's say, summarize all the results that we've seen so far, so we saw that basically the thermal behavior of the building together with the energy performance can really be modified if we consider the modification of the climate that will occur in the next year. So from the past 90s to the, let's say, up to 2080 years, according to the projections of the IPCC. What we can see by summarizing is that we are going to have a huge overheating of outdoor temperatures, which will, of course, generate indoor thermal discomfort into the environment, because we have, let's say, more than 4 degrees difference in between the years. And then this is confirmed also outdoor, because the microclimate simulations showed over 4 degrees of difference from now to the future. And of course, we will have a decrease of the heating need, but we will have a huge non-negligible increase of the cooling energy needs. So this is something we must take into account while, let's say, providing or highlighting, identifying some strategies to mitigate such phenomena, which must be, let's say, mitigated from the outdoor, but also from the indoor, while, I don't know, designing some strategies to retrofit the building and so on. After this part, I wanted to show you some work in progress, because so far I talked about numerical activities, let's say some modeling activities, but we are also doing a lot of experimental campaigns in order to calibrate such models. So what we did for the specific purpose of this project is to develop a new monitoring equipment, which is shown here, and which consists of a sort of environmental payload. So a set of miniaturized sensors which are combined all together, and which can be mounted both over a helmet, so you can go around and measure different parameters, but it can be mounted also over a drone, so it can collect such parameters at different heights. And such parameters are summarized here in the bottom part of the slide. So we have temperature, relative humidity, air velocity and direction, solar radiation, illuminance level, air quality in terms of VOC, CO, and CO2 concentration. And then we have also an IR camera and a visible camera, so that we can generate maps that are, let's say, representing the trend of such parameters in space and in time. So what we are doing both in Gubbio and in the other case studies is we are going around, both like flying with drones and just walking around wearing these sensors, and mapping the trend of these parameters over time. So for instance, we can get graphs like this. So we have, we did a sort of work in the Gubbio city center, and we plotted all the trend and the variation of such parameters in the proximity of all the buildings to see and to understand and quantify the local variation of such parameters over time and over space. And this we are doing also in Crete, so in the other case studies of the project. These are some pictures from the experimental campaign carried out in Knossos by drones, when we mounted all these sensors. And here again we can see the different paths at different hours during the day that we, let's say, we analyzed, and we plotted air temperature, relative humidity, solar radiation, wind speed, and the CO2 concentration in the different parts of the site, of the ArcGIS site, so that we can see really which is also the part which is much affected by a particular overheating phenomena, where there is too much relative humidity for, I don't know, the heritage conservation and so on. So this is really useful for the purpose of the project. And I thank you for your attention.
Okay, thank you very much, Veronica. Let's come now to the third presentation. All right. Non sta registrando? È rosso. Non so, ci piglio. Questo stanno vedendo il video tutto quanto? posto, no? Okay, sorry for the interruption. We're just checking technical details. Okay. All right, thank you very much. So this is the last talk of this virtual training course. I try to stand. I hope that people online will be able to hear me. We are now getting into the structural aspects of the work we are doing at University of Perugia. So let me first acknowledge my co-authors working with me in the structural part of this project at University of Perugia. So most of all, Dr. Cavalaghi, that is hardly working in this project with me, and also Professor Busella and Professor Materazzi. So what I will show you here is what we have been doing and what we are doing right now in the site of Gubbio for this project from the structural point of view, with particular emphasis today. I will focus on the Consoli Palace that you have already seen in the previous presentations. So let's keep the outline and let's get into the interesting aspects. You've seen already that for this building we have performed an architectural survey, including the pattern of the stones on the different facades. This was already covered in the previous presentation. What I would like to stress now is that from the structural point of view, it's very important not only to make a survey of the geometry of the building, but also of cracks and damages that are present in the building. It's a masonry building, so of course it is natural that the building exhibits some cracking patterns due to different loads acting on the structure, dead loads, but also these cracks could be the result of past earthquakes that could happen in the past. So here, for example, you see the crack that we have found in the building in this section. This is the noble floor. This is the Arengo Hall in the main entrance of the building. You see, for example, in this diagram here, this crack that is visible in this picture on the left. The same for this crack here that is also visible there, and also this crack starting from the key section of the arch that is visible in this picture. Other cracks that you see here, again this big one here that is related to the circumstance that there is an arch inside this wall. And the crack, of course, shows you where the arch is actually hidden, and you saw it in the picture here on the left. And other cracks in the loggia that you see here in this plan view, and other cracks in the vaults on the top of the building related to the thrust, the horizontal thrust of the vaults themselves. And of course cracks in the main facades of the structure, like this is the facade on the east side, the most important one, that is cracked. And at the end I will show you some numerical results that try to interpret the origin of these cracks and try to select which ones are probably caused by vertical dead loads and which ones are instead probably caused by past earthquakes. So most importantly, we have seen from the first presentation by Mario Costantini that from satellite we are able to see some slow movement that have occurred in the last years on the building. What is very interesting of that technology is that it can go back in time because the raw data is already stored somewhere, and it can be processed even after years that the data have been collected. So we are able to go backward to understand what's happened in the last years. And this data highlight that there is a very slow movement of this corner of the building. We are on the north facade. This corner of the building is apparently this is absolutely possible because there is this vertical crack on this north facade of the building that is absolutely compatible with a local overturning, possible overturning of this corner of the building, which is also the case of other cracks that are present in the west facade. So as we will see in a few slides, we have installed a structural health monitoring system in the structure to try to understand if something wrong is going on and possibly anticipate any major problem, any major collapse. So the idea is to go from the very large scale, from the satellite information to the local scale, to the critical building that is investigated from different points of view, as you've seen in the previous presentation. Materials degradation that is related to climate forcing, climate effects, and structural damages. Here you have first some preliminary information about the diagnostic activities being carried out on this building. So first of all, to characterize the global behavior of the building, we have performed ambient vibration tests and model identification tests. So ambient vibration tests are tests where you put vibration sensors over a structure and you record the vibrations of the structure under normal operational conditions, so without any artificial loading. And from these vibrations, if the measurement is properly done, and of course if the hardware that you use is appropriate, you can extract important information on the behavior of the structure, and most of all you can extract the model properties of the structure, so natural frequencies, damping ratios, and mode shapes that tell you a lot of things about the global behavior of the structure. So in this ambient vibration test we have instrumented four main levels of the structure, essentially the four rigid floors or almost rigid floors that are in the structure. So the first level is this one, the Arengo hall, then you have the noble floor, and you have the top of the building. We used 4 accelerometers per floor. If the floor was rigid, 3 would be enough, but we selected 4 to be able to understand if the floors behave rigidly or not, because the building is very large, so the formation in the plan of the floors is absolutely feasible. So here you see all the sensors installed in the building, and this is the main results in terms of signal processing of this data. These are singular values, the first 3 singular values plotted against the frequency, extracted from the singular value decomposition of the spectral matrix of the acceleration measurements. So essentially this transform gives you information on the model frequencies. You have, as it is well known in the field, you have under certain hypotheses, you have that the first singular value line has maxima, local maxima, at the frequencies that are the resonant frequencies of the structure. So you see here that in the range from 0 to 10 Hertz, we are able to identify clearly at least 6 peaks that are associated to 6 linear normal mode of the structure. And here are the mode shapes of these linear normal modes that we have classified into flexural mode shape, so with F, local mode shape, and I will tell you how we have been able to say that this is a local mode, and torsional modes. So essentially the modes that we identified are the first bending or flexural mode of the building along the weak direction. The second mode is bending with a little bit of twisting, but it's actually bending in the strong direction of the building. Then these are 2 local modes, L1 and L2, and then we have the global torsional mode of the building, and again another local mode of the building. How can we say that these are local modes? Because we have constructed a numerical model of the structure that I will introduce you later on, but now I anticipate some results because I need them to discuss these results. And these are the mode shapes predicted by the numerical model. For some reason the last one is not animating, but you can understand pretty well, for example, from mode L3, that this is a torsional mode of the small bell tower that you have on top of the building. So since we were not instrumenting the bell tower of the building, we are able to identify the mode shape components only where we have a sensor. We didn't have sensors on the bell tower, so we are not able to see this kind of movement, even though we are able to identify the model frequency of this mode. And the same, we could say, similar comments for L1 and L2. Here are animated mode shapes of what we have identified, from where you see that actually the first two are global bending modes, and the fifth is a torsional mode. So after this diagnosing test, after knowing something about the behavior of the structure, after identifying from satellite data what could be the critical aspects of this structure, we have installed a structural health monitoring system on the building. An SHM system is a system that consists of sensors of different nature that measure quantities of different physical meaning, and try to use these information, these records, for anticipating problems in the structure, possible damages, understanding if the structure is damaged after a critical event, such as an earthquake. Of course, when this damage is not visible from a simple visual inspection, because we want to see a damage when it's actually at its very early stage. So the SHM system that we have installed within this project is very simple. It's essentially, it comprises 3 accelerometers that we have put on top of the building. Why on top of the building? Because there we are able to putting the accelerometers there, we are able to observe all the linear normal modes that we have identified from the ambient vibration test. So we are able to identify the natural frequencies of all those 6 modes. And then we have 2 linear variable displacement transducers that are actually transducers that measure displacement between 2 points. And those are placed across 2 major cracks in the building. One is a crack that could be associated to an overturning of the loggia with respect to the Consoli Palace. Here we don't have any evidence from satellite, but this is engineering judgment. We know that the loggia could be a weak part of the building. It's funded at a level that is lower with respect to the funding level of the main building, and actually there are cracks that evidence this possible movement of the structure. Instead, the other crack that is here on top of the building is placed on a vault, and it's on the corner that could be moving from what we see from the satellite. So the accelerometers acquire data continuously in time, so 24 hours a day, and for the whole year. These data are acquired with a specific sampling frequency that in this case is 40 Hz, and this data is used for some processing that now I will introduce. The static data instead is acquired with a lower sampling rate. We don't need to acquire amplitudes of cracks in a dynamic way, so we acquire one single point every 30 minutes. And the same we do for temperature, because every linear variable displacement transducer is also placed together with a thermocouple, so a sensor that measures temperature on the masonry, because there is a correlation, as I will show you in a while, between crack amplitude and temperature of the building. So for the processing of the vibration data, this is the procedure we have developed in the last years in our research group. Essentially what we do is we perform automated model identification. So from this data we extract the model properties, essentially the natural frequencies. We are mostly interested in the natural frequencies. Natural frequencies of buildings are potentially sensitive to damage, but the problem is that they are also sensitive to environmental parameters and to changes and fluctuations in environmental conditions. So we have to remove these effects, which we do by proper statistical modeling. A very nice way of removing these effects is by principal component analysis. That is a technique that does not require actually to measure the environmental quantities to which natural frequencies are correlated. And after removing these environmental effects, we obtain these so-called residuals. So why are the natural frequencies identified from the vibration data. Y hat are the natural frequencies estimated from a statistical model that takes into account temperature fluctuation. So if you take the difference between these two, you get a quantity that is essentially insensitive to temperature and humidity fluctuations, because essentially you model those aspects here. So when you take the difference, you eliminate this effect, but you potentially keep the possibility of tracking changes in the structural behavior in the form of stationary changes in the natural frequencies. To detect these anomalies, these changes in the structural behavior, we compute a classic statistical distance on the residuals, that is the t-square statistic. That is a scalar quantity that gives you immediate evidence if the data are deviating from their past trend. Here is a graphical sketch of what we do. Essentially, this is the removal of the temperature effects, and this is the control chart based on the t-square statistic I was showing before. So if you compute this t-square statistic or another statistical distance, it makes no difference. You have a process like this. You need a training period, an initial period in which you acquire data that you need for training the statistical models that are behind these results. And after this training period, you enter into the monitoring period. And if the process remains with the same properties, which means that the statistical distribution of, in our case, natural frequencies has not changed, you clearly see that there is no main difference between the situation during the training period and during the observation period. But when you have a change in the structural behavior, then you have also a change in the statistical distribution of the residuals, and this you clearly evidence in the form of a jump in this statistical distance. So you have, for example, if those lines represent confidence intervals, like the 99% confidence intervals computed on the statistical distance during the training period, it means that if the process remains under control, you just have 1% of points that are outside of these thresholds. But if the process changes and there is an anomalous behavior in the process, then you have more than 1% of points outside of this threshold, and maybe, like in this case, you have 100% of points outside of these interval. So to give you an idea of what we are actually able to obtain with these techniques, here I show you a result that is not taken from the HERACLES project, but is illustrative. This is a bell tower in the city of Perugia. It's actually a very symbolic monument for the city of Perugia. It's the bell tower of San Pietro. This structure has been monitored by our research group at University of Perugia since the end of 2014, and still continuously monitored, such as other cultural heritage buildings in our region. And this tower was, of course, exposed to the recent Central Italy seismic sequence that, as you know, occurred mostly in the second half of 2016, with also a little bit of earthquakes at the beginning of 2017, unfortunately. Actually in Perugia we are very far from the epicenters of the main shocks of this sequence, because we are about 70 kilometers far as an average from these epicenters. But the three main shocks of the sequence were clearly felt by people in Perugia. First one was on August 24th, second one was October 26th, and the third one was October 30th. That was the strongest. But actually the responses that we recorded on this structure, like in every other building in Perugia, were not very high. I mean, no major damage was observed in any building in the city of Perugia. The earthquake, we felt the earthquake, but was absolutely a weak earthquake for our city. But if you look at the control chart built on using the data acquired by the monitoring system on the bell tower, you see here the first year of monitoring period. We typically need 1 year for training period. Then you see the monitoring period, and you clearly see that there is a jump in this statistical distance, these green points, after August 24, and another jump after October 26 and 30th. And this jump is, remained steady up to a few weeks ago. and clearly highlights that the structure has undergone some permanent, even though very weak and slight damage that we do not really see from outside, but we can clearly reveal with these methods. Of course, if you go inspect the natural frequencies and not the residuals as we do in the control chart, you are not really able to see the frequency decays unless you go very locally and you take a detailed view around the event. You don't really see the changes in the natural frequencies because you see that there are very large seasonal fluctuations of natural frequencies associated to change in temperature, and also daily fluctuations of natural frequencies associated to change in temperature from day and night. So even though there is actually after August 24th, you can see that there is some jump in the average value of the natural frequencies. This is not the proper way of trying to detect these anomalies. All right, going back to the Consoli Palace, we started with 10 minutes delay, so I anticipate students in the room that we will also finish with about as much delay. So here you see some data taken from the monitoring system. I start with the static sensor, so the linear variable displacement transducers. This is the first sensor that you see here on this crack between the loggia and the palace. You see here what we have recorded since the installation of the monitoring system that was completed at the beginning of July 2017 up to a few days ago. You see that this crack was actually opening a little bit and then it was closing, so a negative displacement, and it's actually closing these days with a total amplitude, with a total displacement that is less than 0.1 millimeter, so a very small displacement, but the sensor is very accurate. In the bottom you see the temperature recorded by the temperature sensor that is installed here nearby the LVDT sensor. You clearly see that there is an apparent, an evident correlation between the amplitude of the crack and the temperature, and in particular while the temperature decreases, the crack tends to close. And this is of course associated to thermal expansion, in this case to a reduction in the volume of the masonry associated to a reduction in temperature. The same we can say about the crack that we are monitoring on this top part of the building that is actually opening, in this case closing a little bit more. This is the one that we suspect could be active from the satellite data, but hopefully it will not be the case. The amplitude of the crack was a change of about 0.2 millimeters, and again the crack is closing under decreasing temperature. Here are the accelerometers that are placed on the structure and that are continuously in operation. Those are installed at the base of the bell tower on the top and on this corner on the top of the building. Of course, they are protected from water and they are isolated from the masonry through a plexiglass block that helps preventing problems from lightning shocks. Actually, since the beginning of the monitoring, we already had damage on the monitoring system due to a lightning shock. So even though we took all the necessary actions to prevent this kind of damages, you are never able to put the risk at zero. And every time a problem like that happens is unfortunately a significant expense of money. I will not say how much because this is not elegant, but it's like that. It is the case. So here you see some earthquakes that we recorded before the final installation of the monitoring system. We were putting the sensor on the structure for diagnostic purposes even before the installation of the monitoring system. While here you see a typical 30-minute recording. We identify the natural frequencies and the model properties of the structure every 30 minutes. So we take records of 30 minutes. And you see that every 15 minutes there are bells ringing on top of the building with certain number of rings. Like here, you see a typical bell ringing. This part of the signal has to be removed because it's not appropriate for model identification, so there is some pre-processing of the data that is necessary to do. And here you see the tracking of the 6 natural frequencies that we identified in the ambient vibration test. You see that the values of these natural frequencies are pretty stable in time. There are no big temperature effects, even though if you take a closer look, you clearly see the fluctuation of the natural frequencies every 24 hours, associated, of course, to temperature changes between day and night. We have already built a control chart from this data, even though the training period is actually not sufficient to characterize fully the changes in environmental conditions that you have in 1 year. So these are very preliminary results. So with a training period of 2 months and then an observation period, you see there are no anomalies, even though these charts will be a lot modified in the future. You just have a small trend here that you see in the statistical distance after, let's say, the first mid of September. By the way, here there are 3 days where we don't have data. This was the lightning I was mentioning. You can check that we had a strong, actually it was last rain we had in this region probably up to today. And you see there is a little bit of trend here. This might be associated to the fact that there are some works going on the structure, and in particular on the roof of the loggia, but this is just a guess. So going to towards the end, of course, to understand really what's going on a structure like this, we need to perform structural analysis, and the way we do that is by finite element modeling, among other approaches. So we have developed a three-dimensional finite element model of the Consoli Palace building. To develop such a model, we need to start from a three-dimensional model of the structure, so a CAD model of the structure like this one. And in this modeling, we also include the effects of the soil, because we are interested in understanding if changes in the water content of the soil could be, which is of course associated to climate change, could be dangerous for the structure. Here you see the structure, and this red part in this part here is the interface between the main building and the soil. These are the finite elements used to discretize the building. Essentially, we have a structured mesh in the soil. Also, some parts that, due to irregularities, are reproduced to an unstructured mesh. And for the building, we have an unstructured mesh with this kind of finite elements, tetrahedral elements for the structure. And here, for example, you have a detail of modeling of the bell tower. Here are the modes. I already showed you these modes, so I will skip this. I just would like to mention that we have a very good agreement between experimental and numerical natural frequencies. So these are the natural frequencies identified in the ambient vibration test, and these are those predicted by the numerical model. And the error is overall very small, with some cases that need a little bit of tuning. We are working on this, but we start already from a good agreement between model predictions and experiments. To understand the origin of the major cracks that are in the building, so the damage that you can find today in the building, we need to perform, of course, nonlinear analysis in the post-elastic range. So we need to reproduce the behavior of the masonry in both tension and compression up to the limit of the elastic state, and of course in the post-elastic range. And to do so, we have implemented a classic nonlinear concrete damage plasticity model, that is a model that is widely used to reproduce the nonlinear behavior of masonry. And here I show you some results related to different analyses we have performed on the structure. Essentially, I'm showing you two kinds of results. First type is an analysis under, both are nonlinear static analysis. The first one is under dead load, so self-weight. And the second one is under horizontal load, so a pushover analysis, as we call it in earthquake engineering, trying to reproduce through a static analysis the effect of an earthquake. So here, for example, you see these cracks that I was mentioning at the beginning of the presentation. So these cracks are originating from a detachment of the lateral walls from the main building due to the thrust of the bolts. And after performing a nonlinear static analysis under self-weight in this local part of the structure, you see that we have the appearance of these cracks that are fully compatible with what we see here. So the problem here is that the thrust of the bolts is not sufficiently removed by means of tie rods, for example. We also can find this clear shear crack over this arch. This is the loggia. On the right you have the main building. And since the loggia is funded at a lower level, it's deforming in vertical direction more than the main building, also because it's less stiff. And this means that there are shear forces acting on these horizontal parts of the loggia, and you have this shear crack that you find from both the numerical results and you also detect on the structure. And finally, I show you some results of this pushover analysis, so a linear static analysis with horizontal forces that act in the weak direction of the structure. So this tries to simulate the effect of an earthquake that makes the structure move along its weak direction. And you see here the total shear force at the base, and here you see the displacement of a control point of the structure. If we increase the horizontal forces, we see that some cracks start to appear here. If we increase the forces more, you see this clear vertical crack, and you might remember that these two vertical cracks on this north facade were at the beginning mentioned as very critical because those could be associated to the movement we see from satellite, and these results tend to confirm that the initial origin of these cracks could have been a past earthquake that the structure has suffered. And if we increase the force, again, you see that this crack increases. And after a certain point, we start to see cracks also on the main facade. So with an earthquake pushing the structure along its weak direction, we see some cracks also on the facade along the strong direction. And these cracks, if you go and look in details, some of these cracks, like this pattern that you have here, it's more or less visible also on the crack survey that we have performed, and especially here that we have force level. So with this I conclude. We have, with this virtual training course, we have proposed an integrated approach for cultural heritage management. These conclusions refer mostly to the structural part, but to summarize, we have seen how from satellite radar information we are able to select critical buildings over wide areas, buildings that show possible critical movements. Then we go in the field and we inspect those buildings. If these buildings are cultural heritage, important buildings, then we are even more motivated in doing this. We inspect the structure from different points of view. We try to detect the presence of possible damages and the material degradation that could be associated to different causes, and we try to understand what is going on. So for material degradation, we try to see what is the link with climate conditions. And for structural damages, we try to understand if those are due to, for example, vertical loads or earthquakes. And with SHM systems, we try to understand if some of those damages are actually active damages that could lead to a failure in the future, which of course we want to anticipate, to take the necessary actions to prevent these collapses. Of course, let me acknowledge again the European project HERACLES that is funding this study. That is a very big project involving 16 different partners, as you've seen already. And regarding the structural research being carried out at University of Perugia, I would like to acknowledge also contribution of 2 PhD students that have been working on, are still working on these topics, and a few master students that have worked during their thesis activities on this subject. There will be more to come, even PhD students that have just started, and master students that are ongoing with their thesis will give us more help. Thank you very much for your attention. So with this, we close also the web connection. So goodbye, everybody.